Hi everyone, let's talk about filtering and aggregation. I'm going to probably crank out a couple of these lectures today, just trying to finish off most of the lecture series so we can actually have more time to talk about your projects later on in the term, in case you see the same outfit multiple times. So let's get started with what we're going to be talking about. So filtering and aggregation, it's actually directly related to what we were talking about earlier in the term. One of the things that we normally, when I talk about filtering and aggregation, I'm talking about visualizations doing it, as in the data's still there, but you're just hiding it or aggregating data. That doesn't necessarily have to be the case when you're talking about data in general, not just the visualization. So it could be just removing data itself, or removing the data that's returned to the user from the back end, that sort of thing. Or we could be aggregating on the fly and getting the data that way. So I'm hoping that you guys think about ways that this could be generalized to other things beyond just the visualization itself. But we're going to learn about what the differences are between filtering and aggregation, ways we can do it, why we do it, and what kind of visualization techniques we can use to try and indicate this. So the big thing to go over right away is what's the difference between the two. And some of you may know, some of you may not. The idea of a filter is I'm going to remove stuff. I'm going to remove what is presented. It doesn't mean I'm deleting the data. It just means I'm not showing it. I'm hiding some of the data. Aggregation is when you take multiple data sources, either multiple items, multiple attributes, and you sort of squish them down. You sort of, instead of saying, here are all the marks for this assignment, we see what the average mark for the assignment is. You're still providing data, but it's in aggregate. We'll look at a little bit of embedding soon as well, I think. So we'll have to look at that. Embedding, by the way, would be you present all your data, but then you can sort of, you can show more details in certain areas. So you've filtered it out, but you can still drill into the actual details. So for both filters and aggregates, what we can do is we can either filter or aggregate by item. So remove all students that are, remove all ITEC5207 seminar students that are PhD students, for example. That's removing items. Removing attributes would be remove all the emails and all of the student numbers from the list of ITEC5001 students. The attributes of those students are removed, some of the data that we need. So when I post things for assignments, or when I post things for, let me think of a good example. I'll often post, I think we're posting the information about you guys when it comes to the course projects. And we intentionally remove information that, so, oh yeah, there you go. The seminar that we did, the survey that we did for homework 1. When we did that survey for homework 1, we removed all attributes that were personally identifying you. We didn't remove items unless someone gave us garbage data. Then we'd be removing or filtering the items. Aggregate data, on the other hand, would be things like I'm going to take the average for the class. That's aggregating items. So the average for this assignment was an 85%. Aggregating attributes might be your average in the course is 85%. Each one of those columns ends up being, just say, an exam grade. Well, we can merge a bunch of these exam grades together and get the average for the assignments, average for the homework, or average for the project, average for the exams, that sort of thing. And we looked at complexity. One of the reasons we want to do this is because we want to reduce complexity, because that is ultimately what, when we were looking at perception earlier, we realized that there's only so much you can present at once. That's actually one of the major problems that we have. We can't just, present all the data all at once. It's just, it overwhelms people. Any kind of perceptual pop-out effect that we'd be wanting goes away. We cannot show everything at once, so therefore we have to remove a lot of this stuff. And so one of the ways we can do this is derive new data. That would be something like aggregation. We could change our view over time. We'll look at that very, very soon when we look at faceting. we can show different perspectives of the data over time. And time is a major thing that we can leverage to really help people understand data. The facets would also be, can also be for same view at the same time versus, I think it's Gapminder, where you see an animation of how things change over time. If you see a physics simulation, you can see things, how they change over time. Yes, it's different timestamps of the data. Or we could just change what part of the data we show over time. We also have something called focus plus context, or focus and context, depending on how you want to call it. The idea that you provide the high level information about the data that you're showing. So it might be you show the entire music library. That's the context. And then you show specific information or more focused information on a subset of these data. Or you show all the attributes and you show a subset of these attributes. So focus plus context is you have some data in focus and then you show all of the other items in lower fidelity detail. We'll hopefully get time to look at this. And then finally, the two we're looking at today is deriving new data. That would be aggregation. And the reduction, which is filtering. We remove stuff that we don't need. So in terms of reduction, we're just showing less of the data. It reduces complexity. It's the issue with it is you can often lose track of stuff you hid. I mean, it's a classic case of when you get a piece of information from somebody. Politics is really bad for this right now, so that's why I like bringing it up all the time, right? They won't tell you the context, or they won't tell you the other surrounding information. They reduced everything but other than a number. This many jobs were brought here. This happened, right? It would be like saying the unemployment rate in Canada is ridiculously high right now. Oh my God, Trudeau must be doing a terrible job. Now, whether you believe it or not that he's doing a terrible job, the fact that I left off the fact that it was COVID-19 and everyone has stay-at-home orders, and that's just forgotten, that's a huge piece of information. You can't just reduce. If you remove some information, you can sometimes lose the big picture. But we can also reduce items or attributes or both, depending on how we want to do things. So here would be filtering, right? I eliminate items. Great. Aggregation, I create new items, and then I either show those new items on top of, in addition, but most of the time I remove the old items and put in just the new items, the new created items. Well, filtering, fairly easy to understand. I just remove stuff. It's really easy to compute, just remove stuff, right? I don't have to calculate the average. I don't have to calculate the standard deviation or do any kind of stats. I just remove stuff. But it's really easy to forget elements, really easy to forget the context of surrounding things. Versus aggregation, no data is missing. I just have an aggregate piece of data. But how I summarize it, what I summarize, how do I actually, the calculation time to summarize things, that's a different story. That's actually where the challenge with, this is where there are three types of lies, damn lies, and statistics comes in. That when I aggregate data, the conclusions that you make may not be warranted. The average for this class was an 80%. Oh my God, everyone did poorly. No, everyone got 90%, except for one guy did like a 10% on the exam. Right? Outliers really throw things off, for example, but yet it's covered by aggregate data. So how do we end up filtering? Well, we have dynamic filters. This is, you move a slider and all of a sudden a bunch of items go away. We can filter by item. We can filter by attribute, which I've already talked about. So I'm going to show you a dynamic query very, very soon. So a filtered item removes items based on a particular value. I'm removing all PhD students for the ITEC5207 seminars from that data set, right? It's based on the value that they are listed as a PhD student. I can remove attributes based on, fewer attributes per item. I want removing attributes that are labeled this, or attributes that are below this particular point, or attributes start with the letter I, or whatever the case is. And you might, it's often a good idea if you order your attributes in a particular way. Filtering ends up being a lot better, right? I put all my exams together. I filter out these exams. Or I put all my, where I want to remove all the assignments, I might filter out all the assignments. If I order my attributes visually, it's a lot easier for the user to choose a subset of the attributes to remove. So I like Ben Fry's zip code. You guys may not know much about zip codes because we're not in America right now, but I like bringing it up. So let's see if I can get this up and running. So, okay. So this is types of digit. Boom. That's my old zip code in case you didn't know. But notice what happens if I go 02. I get all of Massachusetts. I do believe that's all of just at Massachusetts. 0, 2, 3, 4, 5. I don't even know where that is. If I go 4, 5, 3, 2, I can narrow it down to 1. Ohio. Nice. In case you ever wanted to know how the zip codes actually work, the entire West Coast is 9. 8. 9, 9. Okay, that's where are we looking at here? Is there anybody? Nobody with a 999. 8. Nope. 7. Not many people in. That is, what state is? I don't know my states anymore. Idaho. Anyways, notice not the population density that you would expect. So 8. There we go. 8. 5. 4. No. 2. Ethel, Washington. Okay. Anyways, that's a dynamic query. Notice that all the zip codes are listed, but you are muting the ones that are not currently being looked at. You get this bright white for the stuff that is in your query, and so you can actually sort of pay attention to where it's located and how zip codes. You'll notice you're not just getting a zip code information, you're getting how zip codes actually work as well. There's other information being conveyed with this besides just finding your zip code or where it's located in the United States. Okay, so let's close that and let's pop up this thing here. But I am filtering, but I don't have to necessarily remove the item. They're being filtered, but filtered just by the light intensity. I'm going from a yellow to a white. So if it's yellow, it's being filtered out, right? I can still show the data, although oftentimes I won't actually show the data. Here would be another example where I get to filter by attribute. I can filter by item. I can show all information about what kind of health code violation it is, where the restaurant is located. I can, well, this is filtering out items per se. I don't think you can do an attribute. You know, an attribute on this one though, where the attribute being conveyed per item changes, and I can show that all boats have the same look, or boats change by different colors, or remove. I don't want to remove boats, particular boats, but I might not. It might not show as much on the glyph itself if I'm filtering out particular attributes. This, by the way, is shipping lines. It was harder to find an attribute filtering, visual attribute filtering, but marine traffic, it's a very interesting visualization of how shipping, like look at this, boats going along that particular river, is actually live, that you can actually see how shipping in the United States and the rest of the world actually works, which I thought was interesting. Here would be something like an attribute filter. Google Maps actually has layering that you put on top of stuff. So I can get a satellite view, but I could also layer on an attribute such as bike paths, then in green, I can show the main road that you're currently on. I can add and remove particular restaurants that are on this thing, so that I'm adding and removing items. So I can filter by attribute. I can also filter by items. There's a lot of different things you can actually do with oh no, sorry, that's the live traffic. That's not so traffic on Wyoming Avenue is actually fine here, except right here, which is where the train crossing is, but there. No, this is just the parkway getting in the way of everything. The point being, there you'll find attribute and item filtering in a lot of places you may not have even realized. So I'd like you to take a step at it, take a swing at this. Choose your favorite dynamic querying system, and it may not be a visualization, but one where you are live filtering in and out things. So you're not pressing the search button, you are essentially moving around sliders and everything automatically adjusts. So a very fast-paced way of searching for things or filtering out things. And I would like you to find your favorite dynamic query system, or at least one that you want to talk about, and your least favorite query system. That's not a dynamic query system. The one that drives you nuts. Does it filter items and attributes? How does it filter things? What is terrible about it? So sometimes finding your least favorite is also as important as finding your favorite. So two things: your favorite dynamic query system and your least favorite querying system in general. And just post your two systems plus your discussion, brief discussion, maybe some screenshots, and put that in the drive folder, the lecture 10 drive folder. And then we'll talk about this in class. In case you're wondering where all this comes in, that we're talking about information seeking and information foraging behavior, scented widgets come in handy. Literally coming from the term information foraging, they took this idea and went, hey, let's put a scent on our widget. Let's make it so that our controls, like our star system that we have here, like what kind of data set we have, like our tree that we're showing here, that we actually are conveying information about what is going on. And I've tried this a couple of times. It's a lot harder than it seems. But you're providing visual cues for when you're doing a search task. You already have this with links. If you go to Google and you click on a link and you go back, what happens? The link has changed colors. It's giving you a scent for what links you've already visited. In this particular case, you can provide scents for the kind of items that people might be looking for, or what other people have looked at, right? The Amazon other people have ordered this item too is a sort of a scent. But if you can have your widgets themselves, like like a scroll bar, provide information for where you're searching or help you find stuff, that's extremely useful. Or where things were more popular or where things were filtered out, can really help you make sense of a large amount of data. Because one of the ways you can filter is just based off of how much data you can show at once. So I'm only showing the first 10 items. So what I want is some kind of scent for where the other items are, or what so if I'm looking for I'm trying to think of a good example. I have a coding example, but that's not going to work for many of you. If I'm doing a search in a Word document and I want to know where all occurrences of a particular word are, well, I can only show so much of my Word document at once, right? So what if I, on my scroll bar, listed or had little highlights on the side of the scroll bar saying where that word popped up in the document, or where there's an error in the document? That would be helpful for, I'm still zoomed in, I've filtered out most of the text other than the little bit that I'm showing at a time, but the scroll bar is actually indicating where that word is occurring in the text. So you can also have interactive legends. So I've selected a subset of the data, and in my legend, I'm clearly indicating what has been selected and what has not been selected, or where in my scroll bar I am currently filtering things by. Here would be another example. So where you can, let's see if I haven't tried this one in a while, so let's see if it works. Okay, it's on the, here. Filter. I love this example just because it's so nerdy, with LexCorp and Stark Industries and Wayne Enterprises all being on there. MomCorp, I have no idea what that is, but if it's from the comic books, but notice it automatically will filter and scroll and reposition everything based off of what is currently selected. And I have a scent for what is available to me, but I know that Rexall is not actually being shown in the data set, but I can add it on. Okay. And I like, if you have a chance, I would like you to watch a little bit of this video. I'm not going to, videos within videos I'm not a big fan of, but have a chance to look at this particular video. It's actually an interesting visualization. It allows you to look, they're looking at who wrote what in the visualization community, what the topic of those visualizations were, and sort of connecting authors with their topic areas with the actual name of the papers themselves. So Mary Chwinski here is working on these particular topics: interactive design, visualization techniques, system architecture, and DC Robbins is also would be connected. George Robinson is over here, also connected. They have co-authored a lot of papers together with polyarchy visualizations. Chris North is over here. They also have, I think, some collaborative work as well. But when I watch this video, and the point I wanted to bring up, when we look at facets, you'll notice that I can slice and dice my data, I can move things around, but I have no idea where I am after a couple clicks. That is the problem with filtering, or one very, very big problem with filtering. If I have a whole lot of data and I filter out stuff willy-nilly, I don't see where I am anymore. And if I don't see where I am in the grand scheme of things, or how I got there, I can get lost. And that's why we do things like focus plus context later on. Okay, data aggregation. Let's just jump over to that, because I'm going a bit slower than I thought. So how do we aggregate our data? Well, we can aggregate by items, fine. We can aggregate by attributes. And we also have spatial aggregation. Now that's a little bit of a weird thing. I think I have a spatial aggregation. So here's an item aggregation. Histogram is a classic item aggregation, right? The number of people that got 80%, they go in one bar. You get one bar for all the people that got 80%, right? That would be, you could just say the average as well, but a histogram, so the number of people that got values in this range, or the number of items in this range, the number of items with an attribute showing this range, the number of items with that attribute in that range, and you just bin them up. And it gives you a distribution of how my data looks. It's much better than just the average. I could just take the average, but the average is going to be about 13, 14. Here the average is going to be about here-ish, whatever that value is. This binning effect allows me to aggregate the data without having to show all the gory details. It still hides some of it, but it can be very, very useful. Box and whisker plot, or box plot with whiskers, is another way of showing aggregate data. So I can say 1/4 of the people are in this group, 1/4 of the people are between here and here, 1/4 here and here, 1/4 in here and here. We looked at that briefly when we looked at statistics. So here would be a series of box and whisker plots, much like this, and it's a bit cleaner, as in I have one little bar showing all the entire range. I don't have to show every single bar or all these different buckets. I get 1/4 here, 1/4. It's essentially 4 boxes, or four bars in a histogram. Here's the problem with it. So here's the data set itself. These little points show the data set from essentially from above. Here is the frequency. Here's the histogram of those data points right here. So they're changing the distribution of the points over time, so that they're all going into these little bars along the center and not evenly distributed as much anymore. Here is the box plot. It doesn't move. Doesn't even start to move. Same thing here, same thing here. Right? We have these huge changes in how the distribution works, and yet the box plot completely ignores those things. It's hidden. If you can do it right, so that your box plot doesn't not really give you the full sort of the full picture here. That box plot has not moved, despite the fact that distribution goes from random to this very barred, very very clumped together distribution. So here's my raw data going from random to clumped. Here's my box plot going from box plot to the same box plot. Here's another visualization technique called a Violin plot. Notice it actually does show how that distribution actually changes over time. If I have continuous data, it works only for continuous, by the way, or data that actually has some kind of distribution. So Likert scale doesn't work very well for this, right? You'll just get sort of the same thing. But if I have things that have a more continuous distribution, a Violin plot is fantastic compared to a box plot. It gives you the same data, same amount of pixel space, but yet conveys a lot more information. So it's a technique that people don't use that often, but they probably should. I like it, at least. If you actually want to have a chance at looking at some of these things, let's plop it up. We can look at some like a notch box plot, which changes the distribution over time. It shows where things are. Box plot unbound, box clamp to the data, a bean plot, a beesworm plot, right? This is a pointillization task where you don't actually count the number of dots there. You estimate, you can visually estimate. I actually have a research paper on this. You can visually estimate the number of dots in these areas, and you get a feel for the distribution without having to count. Here's a scatter plot, but then notice that you're not as accurate for estimating the number of points compared to this versus this. You get a nice clean estimate of the number of points. Notice it actually matches up with a Violin plot quite nicely. And and then you can put some trend lines in there. There's a number of ways of showing how the points are distributed, and these are ways of aggregating your data with a large amount of data, without having to just say the average is this. These are ways of showing the distribution of your points, of your items, without having to necessarily lose that much data. So I love this quote from Mark Twain. It might actually be Mark Twain, unlike the damn lies and statistics quote, which is actually not Mark Twain at all, but people give him credit for it. Facts are stubborn things, but statistics are pliable. I love that. So the idea that your statistics, you can always manipulate things, and you should always be on the lookout for people trying to manipulate these sorts of things. And this is where we get to when it comes to spatial aggregation. Spatial aggregation, this third type. So we can, but all three of them are susceptible. All these aggregation techniques, and filtering as well, are susceptible to manipulation, to sort of someone trying to sneak one by you. And that one should always be on the lookout for this sort of thing. Spatial aggregation, the idea is space is actually continuous, right? There's no, if I have a town and I separate people in the town based on this, well, the downtown core has a lot more people than people out in the suburb area of town, right? The people next to the train tracks, there's fewer people there than right in the downtown core. So how I actually bucket, or how I actually carve up this space, changes how I deal with the data. I can't just randomly choose things. So this is very similar to when we're looking at fields, that continuous fields, or how I sampling effect for a visualization. With spatial aggregation, how I carve up the space changes what the data looks like. So I might say I need 3 to 4 items per group, and then I figure out what that grouping looks like. Or maybe I have this is the densely populated areas, these are not so densely populated areas, this is completely barren areas. That how I carve it up changes data analysis. And this is a modifiable area unit problem. So where I draw the boundaries, if I can draw it any which way, it changes how the data is done. And so I actually need to know how it's being carved up. I can't just giving me the data doesn't tell me something. How I carve up the data tells me something. This brings us to the US election, because gerrymandering is redrawing voting districts to affect election outcomes. It's a very, very important / scary part of the U.S. electoral system. The idea is you actually are trying to, you get a certain number of districts based off of your population. Nothing says how those districts are drawn. So you're trying to get equal representation for each person. That's the idea. But since you can draw the lines any way you want, you get a weird outcome. So this is how you steal an election. So if it's 60% blue, 40% red, about what it is right now, at least according to the polls, what would you expect? You would expect 60% of the votes going to blue candidates, 40% going to red candidates. You'd have proper representative democracy, right? Doesn't work that way. If you just randomly carve it up, like put a horizontal line, every group, and you have a winner-take-all approach, what do you get? Well, you get 5 blue wins, 0 red wins, and it's not representative of your population, right? This is what the fear was when it came to the Senate in the U.S., where the people in the cities in more populated states would overwhelm the vote and the control for less populated states. That's why every single state has 2 senators, irrespective of how many people that they have. So New York State or California, well, California is the most populous state in the union. California has 2 senators, and North Dakota has 2 senators. And Montana has 2 senators, right? There are states that have less than 1 million people, or barely 1 million people. I don't think even Montana even has 1 million. I'm not sure. Versus California has 30, 40 million. It's a ridiculous number. It's radical different, and yet they both have 2 senators with the same amount of voting power. So that's what they're trying to avoid here. But you can also do it so that, despite only having 40% of the population, if the red team, if you will, carves this up just right, what you end up getting is the red group can get 3 out of the 5 districts, despite the fact they only have 40% of the votes. And that's based off of how you break down the problem. So I strongly recommend, just because I think it's funny as hell, there's a great John Oliver, Last Week Tonight with John Oliver video from a number of years ago about gerrymandering. Have a look at it. I hope you don't mind inappropriate jokes, but if you do, stop at about the 6-minute mark. It's all safe up into the 6-minute mark. And it covers gerrymandering quite nicely. But I'm going to cover it a bit more myself. Turns out my former state also is directly responsible for even gerrymandering. It's based off of Massachusetts and the problems in Massachusetts. It's a very old state, and it has a lot of fun problems like this. So where are we here? Marblehead, Gloucester, that's right here. That's Gloucester, and so this is where the salamander for the gerrymandering comes from, right up here. It was designed, it's referring to a man named Gary, which John Oliver talks about, so watch the video, and choosing how you drew the electoral map, that you can carve it up just the right way to try and maximize your benefit. One of the things you can do is you can try and intentionally split up a group so that you have that you if you split up a Democrat, let's say a Democrat district, right? So that let's say it has 60% of the population, but you carve up the line just right so that 30% of the population is on one side, 30% is in the other, in another district, and the other 2 districts have a large Republican district around them. What you end up getting is you would get rid of the votes for that large population of Democrats because they're split up into 2 different groups. You can also pack them together so that they only get 1 vote, or they only get 1 representative, despite the fact that they should be spread out over multiple communities. So the idea is if you carve it up, you can either split their vote to make it so that it doesn't count, or you can pack people together to make it so that they only get 1 district instead of multiple. So these are the kinds of gerrymandering congressional districts we're talking about. Like, look at this thing. You have to actively, you get physics, you actually had to run statistical tests to get something like this, to carve it up just right. This is one congressional district, this thing here, to make sure that everybody either votes the same or you've split people up. I'm assuming that's is to pack everyone together into one group. They're really egregious. Here is another one. This is in San Antonio to Austin, conveniently, right? Packing all the Democrats in Texas together, for example. So this actually does have direct ramifications, because if your member of Congress is in this, you get one vote. You don't get 5 votes like you might otherwise. If you draw the lines right, you can make sure that the other team, no matter if you're a Democrat or a Republican, the other team doesn't get as many votes, and therefore you can control and keep power for longer, which then allows you to elect a president, and et cetera, et cetera. It is very, very concerning. So in terms of attribute aggregation, we can group by similar measures, and we can also do dimensionality reduction, which we've already looked at a little bit, right? We want to preserve the meaning of the structure while getting rid of a lot of those other dimensions. So when we did multidimensional scaling, when we did principal component analysis, where we choose a particular dimension, even if it's made up of multiple dimensions, and say that that's the dimension we're using, we can actually work around not having a certain number of attributes. This is where data mining comes in, finding the primary attributes to describe the data set you're looking at. And so here's average and spread with 2 examples of dimensionality reduction. They're very, very simple, and they hide a lot of stuff. So there'd be. So I would want to do one other, and I might be going a bit long. So you can try this out if you want. Just do the first one, but I like this little exercise just as a thought experiment. But if you want, make another in-class example here. I was involved in a project a long time ago, called Project Gadfly. It never really got off the ground, but I really loved it as an idea. It was a bunch of graduate students, all PhD students, that were looking at Canadian politics. And what's interesting about Canadian politics is we have the Hansard transcripts. This is every single word that's said in the House of Commons. Every word, every question, everything is recorded and transcribed and available to the public. People don't know this, but it is. Every bill that gets passed, everything is kept and on public record. If you could take those transcripts and transcribe and do a sentiment analysis of them to figure out, what people were voting for, their tone of voice, the complexity of their language, whatever the case is, and look at it for each member of Parliament, what would you do? Because the fact of the matter is, the dimensionality is way too high. We have way too many members of Parliament. So what are the pieces of information that you need? Because this is what the House of Commons looks like, where this would be the ruling party up here. The opposition sits immediately across from them. 3 swords width distance, by the way. Interesting. I always find that interesting. So here's your whoever your ruling party is. Here's your opposition, and then you pack the other people in around them. And Canada has a nice color-coded system, but how do you make it so that you can reason about Canadian politics and who your member of Parliament is, or who that's particular, like who the Conservative Party is, what the Conservative Party policies are, how they voted, what they said, that sort of thing. Were they being incendiary? What kind of data would you want to show? How would you show it? And how would you filter out a lot of this information? Because you can't show everything. So what do you show? How do you show it? And do you filter out people? Do you filter out parties? Do you filter out the attributes of the content of what they're talking about? Okay. When I still have to talk about this a little bit soon as well. I want to make sure that we have more time to discuss design, especially near the late stages of things. And since the final designs that we're asking for we have very little time at the end of term to actually correctly spend on design of your system, visual design of your system. I want to make sure that your designs and your approaches are sound. So I'll talk about this more in the live video, but I would like you guys to team up with another group. There's 5 groups. I guess we may have to do a group of 3 as well, or we can do some other combination. But I would like you to pass your idea to the other group, show their visualization sketches, give the elevator pitch for essentially for your group, what you're trying to do, what your task is, and then I want the other team to give you feedback, propose changes, ask questions, like sort of review what you're trying to do to make sure that there's nothing wrong. They should find something, no matter what. No matter how good you do, how good of a job you do, somebody else should be able to find something you can work on. So if you find nothing wrong, then you're wrong, is a nice way of looking at it. And the big thing I want you to think about is, if you look at them using if you get this proposal from another team and they say, we're doing this, we want to, I'm trying to think of a good example. I can't think of a great example here. If you look at other people's projects and you look at, and they're describing how useful it's going to be for group X, Y, or Z, and you look at it and say, no, there's no way in heck people are actually going to do that. So maybe it is, it's a system for professors to look at each individual person in the class to make sure that they're showing up to lectures, right? It's a visualization system that collects their location information, and it shows where every single person is during the lecture, as for the professor to monitor it in real time while they're lecturing. I would say no, it's a terrible idea. Why? Well, first of all, there's a privacy issue, but number 2, the professor's not going to have the time or the willingness to go through all of that effort just to make sure people are attending class. This is not high school, this is university, so therefore you can do your own thing anyways. And on top of that, they're not going to do it live while they're also lecturing. It's too much multitasking, right? So if you have a particular idea, if you don't think that the other team's ideas, may necessarily be that useful, you should actually figure out what would be a useful piece of information or bring up that particular issue. I want to make sure that we're not solving the wrong problems. I want to make sure that our designs and the solutions we're trying to come up with are actually applicable to the actual problem itself, the task domain itself. And so I would like a sober second thought from the other teams, essentially. Okay, with that being said, I'm going to stop here. This is a bit longer than I was hoping for. We're going to get back to this in a second. We're going to be looking at the next visualization talk. So see you soon.